Okay, so this video is going to be on alkynes, and it's pretty chill. There's just going to be an intro, nomenclature, physical properties, and then some preparation of alkynes. A couple of these are reminders and some stuff we have that the knowledge to actually already figure this stuff out. So we'll move pretty quickly, but let's see this guy first. This is the most basic alkyne that there is, and this is also called acetylene. So you might have heard of an acetylene torch. This is the gas or the hydrocarbon that they use to light that fire. Okay, so there are a couple other things that are kind of terms that we want to become familiar with, and that would be like this alkyne right here. I'll draw it two different ways for you. The bottom one is not explicitly drawing the carbon-carbon triple bond or the hydrogen, and so you need to be aware that they exist, right? And that is a terminal alkyne. Terminal meaning the end, right? And this is as opposed to what's called an internal alkyne. And an internal alkyne is where you have it on the inside, just like this, okay? You also have to remember that is a carbon-carbon triple bond, and when you're counting your carbons, you want to make sure that you account for those, okay? So that's pretty much it for like the internal alkyne, terminal alkyne. Those are important to know though, because the chemistry is slightly different later. These two carbons right here, remember, they are sp hybridized. Okay, those carbons having that sp hybridization have the angle. Let me move this real quick. So the angle about this hydrogen carbon carbon hydrogen bond is 180 degrees. Okay, it's linear. It's got that linear geometry. Easy peasy stuff, right? We know this. We're pros at this. So remember, when you do that hybridization, you combine one s and one p orbital. That leaves two p orbitals left over, and that's where those two pi bonds come from. Okay, and so that's why a triple bond is what it is, right? And this is important just so that you know those triple bonds, or I'm sorry, the two pi bonds that exist are in two separate planes as well. So in addition to that information, we have pi bonds are also going to be weaker than sigma bonds, for example, but in the case of an alkyne, there's more of them, right? So it doesn't matter how weak the bond is, if there's more of them, they're still stronger for the most part. So for example, if we have a carbon-carbon triple bond like acetylene, the strength or the amount of energy required to break that triple bond is 837 kilojoules per mole. Now, if we compare that directly to an alkene, that would be analogous to that, a carbon-carbon double bond ethylene, that would be 635 kilojoules per mole. Okay, so of course you have an extra bond, you have a stronger bond. Okay, it's also going to be a shorter bond because there's three of them. They're sp hybridized as well, so it holds the electrons closer to the nucleus. Now on that note, it's for the same reason, you have more s character and the electrons are held closer to the nucleus. This hydrogen right here is acidic, so we don't want to forget about that, and it's going to be fairly easily removed with respect to, I say fairly easily when you compare it to other hydrocarbons, okay? And that's because the conjugate base is stabilized, being that the negative electron pair is going to be closer to the nucleus and stabilized by that positive charge. All right, nomenclature. So nomenclature is pretty much the same as it always is. So this is going to be fairly easy for you guys, hopefully, because we're pros at this by now. But what I'll do is just do two examples, and those are both going to contain all the rules for nomenclature of alkynes. Okay. Now notice the top molecule has an alkyne and an alkene. Okay, so that's going to be one of the rules. And then we've got, I hate my bond angles. I'm kind of anal about bond angles, but at the same time I'm not, because we're not perfect at drawing, but you should never draw those alkynes bent, okay? So those two bonds right there are alkene and alkyne, right? So which one gets the priority? Basically, it's the lower number goes to the first unsaturation point. So the alkene is at the end, so we start numbering from there. Okay. We also want to make sure that when we number, the longest parent chain contains the functional group. Okay, so it's got to contain the alkene or alkyne, or just the alkyne on the bottom example. Okay. Otherwise, it's the functional group, right? So we need to make sure that we contain that. Okay, so in addition to that, if there's more than one alkyne, then what we're going to have is just kind of like we had like a diene, we will have a diene or a triene or etc. Okay. And that's really all the rules for naming alkynes. Okay, so let's go ahead and name that top one first. So I'm going to use pink to number. We got 1, 2, 3, 4, 5, 6. Don't forget about those 2 carbons in the alkyne. And that leaves us 10 total carbons in the longest parent chain containing the functional groups. Okay, so that's a decane before we change any of the suffixes. And then if we number it, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So this will allow us to easily identify where the substituents are. So at the 1 position, we have the ene, the alkene. At the 4 position, we have an ethyl. And at the 5 position, we have the ine. And then at the 7 position, let me just, rather than putting 2 7s, you already know this, but we have a 7,7 dimethyl. Okay? And remember, we're alphabetizing according to that M. All right, so now we got to put it all together and make sure we get it on this page. So the first thing is the 1 ene and the 5 ine. Those go kind of at the end, kind of in between the decane, or they're placed into that order. So we start with the 4 ethyl, and then we go 7,7 dimethyl because the M comes after E. We don't use the D in the alphabetizing. And then we do dec, and then the ene goes first. So 1 ene, 4 ine. Or I'm sorry, 5 ine. Okay, and I always forget to erase that E. So that it's ene, but there's no E at the end of the ene. Okay, so small things. I won't knock you down for that. Obviously, I do it too. So, all right, let's do this one real quick. 1, 2. Don't forget about that second carbon on that alkyne. 3, 4, 5, 6, 7. If you number all of those are all the same substituent. There's 3 carbons dangling off of that, so you can choose any one of them as part of your parent chain. So we have 7 total. That means that is a heptane, right? Okay, so now we start numbering for our functional groups or our substituents. Number 1 is going to be our alkyne, so ine. And then at the 4 position, again, we have 2 of them, so 4, 4. And this is a dipropyl. So not a diisopropyl, it's just a linear propyl group, okay? It's the normal one. All right, so now we got to name this. So it's 4, let's get some more room here because it's going to be long. So 4 dipropyl, and then remember this is the regular propyl group, not the isopropyl. And then we put our hept-1-ine. All right, so there you go. That's pretty much nomenclature of alkynes, and it's pretty chill. You do have to get that practice in, obviously. So the good thing is we know a lot of this stuff, but the more practice you get, the quicker you'll be at it, and then the quicker you can move on to the next problem that is probably going to be harder than nomenclature. Okay? So, all right, so let's talk about the physical properties of alkynes. Let's say we have this generic alkyne where the R group could be whatever you want. there's really no cis or trans, right? And so when it, like for alkenes, there were some scenarios where they were slightly polar, even though they're non-polar overall, but it created differences in the boiling point, right? So, sorry, let me physical properties label it real quick. So, there's really none of that going on here, right? So there's nothing fancy when it comes to the melting point or boiling point. They're just both low, and that's because these non-polar substances have weak intermolecular forces. There's really just the London dispersion forces, or also known as the instantaneous dipole, and so that makes them soluble in organic solvents. Okay, now what else is there? Nothing. That's really the physical properties, so that's cool. We're good with that. The interesting alkynes. There's really only, I mean, there's some hormones that have alkynes in them, but I'll just tell you my favorite, and that's the histrionicotoxin from the dart frogs. Because dart frog, so here we go. Oh no, that's a Kermit. My bad. Here's a dart frog, I think. It's a colorful frog. Colorful in nature is usually kind of scary, right? Don't touch it, because it'll make you go night-night sometimes. The histrionicotoxin, though, it kind of messes with your nerves, and so it affects your muscle contraction, and I think it's like kind of makes you rigid, a prolonged muscle contraction, which is not good, right? So anyway, this is a really cool structure because it has two fused rings together. So these are two chairs, right? Fused together, and the bottom one has a nitrogen within that, what usually is the cyclohexane ring, and then it's also got some alkenes and alkynes in it. So overall, just a really cool looking structure, and also is kind of just cool in nature. So colorful frogs, some of them you can touch, some of them you can't. So I don't know how to tell the difference, so I just won't touch any of them. Anyway, so the last thing we want to talk about is the preparation of alkynes. So we already know this stuff, right? We've been doing this for days, but I just want to remind you a couple of things. So that was a few chapters ago that we were making alkynes. And so remember, sorry, you hear my kid? She's having a tough time. So, anyway, we got this alkyne, right? So here's that retro analysis arrow. How do we get to that alkyne? And here's one possible way. You can have two chlorines on the same carbon, or if you wanted, you can have those chlorines on two different adjacent carbons. Okay, it's got to be the right ones though, right? The one where we want to create that double bond. And this one right here, remember these chlorines are twinning, right? They are geminal. And these chlorines right here, these guys are neighbors, and so they are vicinal. And we would call them vicinal or geminal dihalides, right? So dihala. Sorry. Dihalides. Okay, so there we go. So we got our geminal and vicinal dihalides. Now, how do we get to the alkyne product? We just add two equivalents of sodium amide, and so NaNH2. Okay, so it's, again, I'll remind you, like I did before, keep an eye on that NaNH2. Don't confuse that with NH3 because it's very different. NaNH2 is a strong base, and so is potassium terbutoxide, this one right here, with DMSO, and it will do the trick to do a double elimination, essentially, to create that alkyne product. Okay. So now that we're much further along in the class, the question is not going to be like, how do you make, what happens when you have this dihalide and you make this, like, what do you get out of it, right? So that was the question a few chapters ago. Now that we have all these tools in our toolbox, we want to know, how do you get from this alkene to this alkyne, right? So let me make sure I get all my carbons right. That's 1, 2, 3, 4, 5, 6. Okay, so That's the question. And I wrote 2 arrows because I'm basically telling you that there's multiple steps here required to get from the alkene or alcohol to the alkyne product. Okay. And we need to know how to do this. So the question you want to ask yourself is like, okay, what is this product? How do I know how to make this product? What do I need? Well, you don't know how to make it from an alkene or an alcohol, but you know how to make it from those dihalides, right? So how can I get from the alkene or alcohol to the dihalides? Well, what you do is, on this one you add bromine, and that creates this dihalide here for you. And after the addition of 2 equivalents of sodium amide, then you get your alkyne product, okay? Now, the bottom one takes an additional step, and think about it for a second. Oh, so let me mention this real quick. So this, remember this terminal alkyne, it has a proton there, and that proton's acidic. That if you add a 3rd equivalent of sodium amide, you can swoop on that proton, right? And what you're going to get is an acetylide, which is that negatively charged carbon ion. And it's very polar, right? Because it's got a negative charge. And the original alkyne is very nonpolar. So what does that mean, really? This is synthetically useful because, I mean, it is water soluble, but let me phrase it a different way because just because this alkyne is soluble in non-polar solvents or organic solvents, right? And the acetylide ion that forms after the additional base is insoluble in organics. And so that means what you're going to get is a precipitate of the acetylide, and that's a great way to purify your compound, right? And so just a nice way of cleanly forming and also driving the reaction forward. Okay, so how do we get this alcohol to an alkyne? Well, first, what you want to do is add a strong acid with a non-nucleophilic conjugate base, such as a paratoluene sulfonic acid, and that gives you your alkene after the loss of water, and then from there, it's the same as the problem above. And so that's all, folks. Let me know if you have any questions. Have fun with it. Synthetic chemistry is dope.